Okay, these are going to be our notes on related rates. So first we want to talk about what are related rates. We use related rates when we want to find the rates of change of two or more related variables that are changing usually with respect to time. In other words, when a quantity changes as time progresses, how does that change other quantities that are associated with it? In other words, how are these rates related to one another? So, for example, when you use a hose to fill some kind of tank, it doesn't matter the shape for the moment. It can be a rectangular tank, it can be a cylindrical tank. If you're using a hose to fill that tank with water, you're increasing the volume of water in that particular tank. Well, what does that do to the water level, for example? I mean, if you're increasing the amount of water, meaning you're increasing the volume, you're also causing the water level to rise. Well, how fast is that occurring? Well, it depends on, how fast the volume is changing. And when you start talking about how these two increases or decreases are related to one another as time progresses, you're talking about a related rate. Another example, if a video camera is filming a rocket launch, how fast is the rocket's altitude increasing? Well, if you're filming the rocket launch, you're going to have to tilt that camera to follow the rocket as it goes into the air. Well, how fast do you have to tilt that camera in order to follow that path? So these are just a couple of the many examples. In fact, we'll take a look at a couple examples that contain these kinds of questions. The thing to keep in mind with related rates is that all functions are functions of time. Most of these are dynamic quantities, meaning they change as time progresses. You're filling a pool with water. You are launching a rocket. This is not the kind of situation where you, let's say, build a fence and look at its area. Once you build a fenced-in area, it remains the same regardless of how far time progresses. But when you're talking about a rocket launch, its altitude changes over time. So those are related rate problems. And if all the functions are functions of time, that means all the derivatives have to be with respect to, that's right, time. So when we take these derivatives, that implies that we're going to end up using implicit differentiation in order to take these derivatives. The steps we want to use in order to solve some related rate problems are: we want to draw a picture if we need one. Many times you will, but not in every situation. Identify what is known and what is unknown. You have to know what you know and you have to know what you're looking for. You're going to label them appropriately in both the picture and using the correct derivative notation. You then need to find an equation that relates your knowns to your unknowns. Once you have that equation, you'll be able to take the derivative of that equation, but the thing you have to keep in mind is that these will be derivatives with respect to time. You're going to be using implicit differentiation in these. We will then plug in all of our known quantities and solve for our unknown. We may have to do a little bit of work to find all the known quantities, but we should be able to find all of them. Usually the best way to deal with related rate problems is just to jump into some examples. So let's take a look. An inflating balloon. Air is being pumped into a spherical balloon at a rate of 4.5 cubic feet per minute. Find the rate of change of the radius when the radius is 2 feet. So if you think about it, when you have a balloon and it has no air in it whatsoever, and you start to blow up that balloon, the radius or the volume, both of those quantities increase extremely quickly in the beginning because it goes from a completely deflated balloon to an inflated balloon. But if you then look at how quickly those quantities are increasing, a few seconds later, they're not increasing nearly as quickly because your balloon is already close to its full expansion. So this particular balloon is going to be a spherical balloon. So we don't necessarily need a picture for this one, but I'll go ahead and draw one just in case. So spheres, three-dimensional circles. Okay. We know that air is being pumped into this balloon at a rate of 4.5 cubic feet per minute. Now we need to figure out what that represents, and there's a couple of clues for that. So when you see this cubic feet, okay, the other way to write cubic feet is feet with a cube on it. When you talk about anything in a cubic measurement, what you're talking about is how much the three-dimensional object holds. How do we know it's 3 dimensions? Because it's cubic feet. So if you're talking about how much a three-dimensional object holds, you're talking about its volume. So when we see 4.5 cubic feet, you're talking about something to do with its volume. But we can tell that this is going to be a rate. There's 2 ways we know that. First of all, I actually used the word rate. But second of all, this is not just 4.5 cubic feet. It's 4.5 cubic feet per minute, meaning this is how that volume is changing as time changes. So you're talking about a change in volume with respect to a change in time, but it's an instantaneous change. So in other words, 4.5 is going to represent our dV dt. 4.5 cubic feet per minute. Okay, so that's dV dt in this problem. That is how quickly our volume is changing per minute. What we're asked to find is the rate of change, so we are in fact looking for another derivative, of the radius when the radius is 2 feet. So we're looking at how quickly our radius is going to change. So that is dr dt. That's our unknown. But specifically, we're going to look for dr dt when that radius is 2 feet. Okay? So in general, if you think back to previous sections, when we have asked you to find a derivative evaluated at a certain number, generally first we find that derivative and then we plug in that number, because dr dt is going to give us the rate at which the radius changes with respect to time for all times. We're specifically looking for when that radius is 2 feet. So we have completed the first couple of steps. We have our picture, we have our known, and we have our unknown. What we then need is an equation that relates our knowns to our unknowns. We need something that relates the volume to the radius. Well, given that this is a sphere, the volume of a sphere is 4/3 pi r cubed. That's just the equation for the volume of a sphere. So notice that's the relationship between v and r, but now what I need is the relationship between dv dt and dr dt. So that means I'm going to need to take the derivative of this equation with respect to time, because both of these quantities are changing with respect to time. V is a function of time and r is a function of time. So if v is an entire function of time, its derivative is the derivative of the volume with respect to time. It's dv dt. For the derivative of the right-hand side, I'm going to leave out the 4/3 pi. It is a constant, so I can go ahead and leave that out of the derivative. And then take the derivative of r cubed, keeping in mind that, again, r is an entire function of time. R is r of t. So when we take its derivative, we drop the 3. We don't touch that inside function of r. We raise it to the new power of 2. But now you need to multiply that times the derivative of that inside function. So that's dr dt. This is where implicit differentiation becomes very important. So we're going to clean that up just a little bit. dv dt, when you take the 3 times the 3 in the denominator, those are going to cancel. So we will get 4 pi r squared times dr dt. So this is the relationship between how the volume changes and how the radius changes for all times. So we know that dv dt is 4.5 cubic feet per minute. We have it 4 times pi. The radius at this one particular moment in time, I don't actually know what the time is, but I can tell you the radius at this time is 2. So that's radius squared times dr dt, which is our unknown. Notice that's the only thing left in this equation that I haven't solved for. So we go ahead and solve for dr dt, which means we'll need to take the 2 squared is 4. 4 times 4 is 16. So we'll take the 4.5 and divide it by 16 pi. And when we do that, it comes out to be approximately, I should make this an approximately equal to, 0.09. And we want to make sure we get a label on that. You look at the derivative to tell you what the label is going to be. The radius is changing in feet, and the time is changing in minutes. So that's 0.09 feet per minute. That's the rate at which the radius is growing. Now think about it for a minute. How did I know it was growing? What sign is my derivative? My derivative is positive. So that means the radius is increasing at a rate of 0.09 feet per minute. It makes sense. The radius of this balloon is already 2 feet. Therefore, it should be growing at a pretty slow rate. So that's the answer to this question, but let me just tack on a little extra thought for a moment. What if instead of asking you for the rate of change in the radius, when the radius is 2 feet, if I instead had asked you when the radius is, let's say, half of a foot, 6 inches obviously, but because we need to keep all our units the same, I'll call it half a foot. How would that change my answer, do you think? Would my radius be changing at a rate larger than 0.09 or at a rate smaller than 0.09? And if you understand the big concept behind this problem, you should be able to tell me that it's actually going to be changing at a much faster rate. But let's verify that using the calculus that we just did. We would still have the same known and unknown. dv dt would still be 4.5 cubic feet per minute. We would still be looking for dr dt. So all of this work that we have is actually going to stay exactly the same even though I've changed your radius. The point at which it's going to change is right here. In this case, if your radius is only half a foot, you're going to take 4.5 and put that in for dv dt and set that equal to 4 times pi times 1/2 squared times dr dt. And then when you go to solve for dr dt this time, what you're going to get, 1/2 squared is 1/4. 1/4 times the 4 just becomes 1. So all you're really left with as far as a constant on the right side is pi. So dr dt is going to be 4.5 divided by pi. And if you put that into a calculator, you're going to get approximately 1.43, and then the label stays the same. That's feet per minute. So notice the rate at which your radius is increasing, and it is increasing because it's positive, is much larger at half a foot for the radius than it is at 2 feet for the radius. So these should make contextual sense based on the application that you're looking at. Let's take a look at another example. A ladder problem. We have a 16-foot ladder leaning against a wall. The bottom of the ladder is 5 feet from the wall before it begins to slide away from the wall at a rate of 3 feet per second. Find the velocity of the top of the ladder after 1 second. What I want you to do is imagine for a moment a ladder sliding down the wall, and think about what that sounds like for a second. When you hear a ladder start to slide, think about what it sounds like. It starts off pretty slow, and then what happens? It starts sliding much, much faster. So when a ladder slides down the wall, when it first starts to fall, so closer to the beginning of time, it falls much slower than it does later in time. So slower, faster, we're talking about derivatives here. So let me go ahead and draw a picture. Okay. We're going to have a 16-foot ladder. So this is my ladder. a 16-foot ladder leaning against a wall. Notice I'm going to go ahead and leave that as 16. That's not really a variable because it's not going to change as time progresses. This is just a static ladder. It doesn't collapse, it doesn't change lengths. The bottom of the ladder is 5 feet from the wall before it begins to slide away. Okay, so before sliding, this is sitting 5 feet away from the wall. And then when it does fall, it's going to slide away at a rate of 3 feet per second. Okay. So we know that that's a rate. Again, you can tell because I use the word rate, but also look at the units. That's feet per second. So this ladder is going to slide away from the wall at 3 feet per second. So we want to call that some kind of derivative. So you can pick whatever letter you want. I'm going to go ahead and choose x. But because that's a rate, this is going to be dx dt equals 3 feet per second. But here's what you want to be real careful of. I now have a dx dt. That is how x changes with respect to time. Well, in order to use dx dt, you need to know what x is in the first place. If that is how x is changing, you have to know what x represents. So I'm going to go ahead and put an x into my diagram. And just keep in mind, this thing started out at 5 feet. So x will be how much farther it slides away. So the length x is actually here. It's how far you are beyond that 5 feet. So then the problem is asking us to find the velocity of the top of the ladder after 1 second. So velocity, that is a derivative. It is a rate. And we're looking for the velocity of the top of the ladder. So if we want to call this distance y, or choose any letter that you like, what we are looking for is how that distance is changing over time. So dy dt is what we're looking for, but we're specifically looking for dy dt at a time of 1 second, so when t equals 1. So notice again, I used dy dt, but not until I had clearly identified somewhere in my diagram what is y, so that I know what I mean by dy dt, or how y is changing. Okay, so that's my knowns and my unknowns. I now need an equation that relates my knowns and unknowns. And given that this is a right triangle, generally what we're going to look for is a Pythagorean theorem. Okay, so that's a squared plus b squared equals c squared in its traditional form, but really it's leg squared plus leg squared equals hypotenuse squared. So my first leg is not 5. Remember that leg, that triangle is increasing in size. So it's actually x plus 5 squared. This will be the length. Plus y squared equals 16 squared. So you have some options from here. You can, for example, take x plus 5 squared and change that to x squared plus 10x plus 25 plus y squared equals 16 squared. And then you can take the derivative, or you can just take the derivative as written. And that's actually what I'm going to choose to do. I'm going to bring down the 2. Don't touch the inside function of x plus 5. Raise it to the new power of 1 times the derivative of the inside function. But this is where you've got to be careful. Remember, all of these derivatives are with respect to time. If this were with respect to x, my derivative would just be 1. But this is a derivative with respect to time. So it's 1 times the derivative of x with respect to time. Okay, so that's the derivative of the first term, plus the derivative of y squared. You drop the 2, you have y to the first power, times the derivative of y with respect to t. And then on the right side, be a little careful. Every once in a while somebody wants to tell me that's 2 times 16 to the first power. Remember, 16 squared is a number. It's a constant. So its derivative is automatically 0. Okay? So now we can start to plug in some of what we know. First of all, I can pull the 2 out of both of those terms and divide it over to the other side. So if we divide both sides by 2, we'll just divide both sides by 2. That will get us x plus 5 times dx dt plus y times dy dt equals 0. So we need to be able to plug in for x. for dx dt and for y. We don't expect to plug in for dy dt because that's what we're looking for. Dx dt is 3. That's the one that's already written here. So the question is, what is x? Well, keep in mind, x is how far this ladder has traveled beyond the 5 feet. So given that this distance changes at 3 feet for every 1 second goes by, we are now specifically looking at its position when t equals 1 second. Okay, so it's in the right labels. So 1 second later, this ladder should have traveled 3 feet. So there's 3 plus 5, which by the way gives you that length of that triangle to be 8, times the dx dt, which is 3, plus what is y 1 second after it falls? Well, we can't use the same trick because we don't know what dy dt is. That's what we're looking for. So we can't find it the same way we found x. But what we can do is use the fact that at this now one particular moment in time, this triangle freezes. To be a right triangle that has a hypotenuse of 16, we now know that the length of this side is 8 because we're 1 second later, and so this side has increased by 3. And the question is, what does that make y? Well, we can use Pythagorean theorem to figure that out. So what we get is 8 squared plus y squared equals 16 squared. Let's see, that means y is going to be the square root of, that's 192. Once you take that, which if you clean that up, that is 8 times the square root of 3, because it's 64 times 3. So that's 8 root 3 in place of y. So we get 8 square root 3 times dy dt, and then that's set equal to 0. So from here we can solve for dy dt. So we'll have dy dt. This is 24. So when you move it over to the other side, you'll get a negative 24 divided by 8 square root 3, which if you clean that up is actually negative, let's see, the 24 and the 8 will cancel to give you 3 in the numerator. So that's 3 over the square root of 3, but when you rationalize, you'll just get square root of 3. If you then need a decimal approximation for that, it's going to be negative 1.73. You'll know whether or not you need a decimal approximation based on how the question is worded. If they want an exact answer, the exact answer is negative square root of 3. If they tell you to round to the nearest hundredth, the answer is negative 1.73. But we do need to get a label on here as well. So again, y is measured in feet, and then your time is measured in seconds. So that's negative square root of 3 feet per second. That's our answer. Now ask yourself this question. Does it make sense that my derivative came out negative? Well, think about what's happening to this y distance. If your ladder slides down the wall, is y getting bigger or is y getting smaller? Well, it's getting smaller. It's decreasing. So it makes sense that its rate of change would be negative. So yes, if this didn't come out to be negative, something would be very wrong. Let's take a look at another example. Filling a conical tank. Okay, this is the filling a tank problem that I mentioned earlier. This one happens to be conical, so we're going to have a cone for this particular shape. So a conical tank will be this shape. The base does need to be towards the top. Think of it like those drinking cups you use when you have a big jug of water. We know that the height of this conical tank is going to be 4 meters, so that's here. And then the base radius is 2 meters. Now we have to be specific about that. The base radius is the radius at the, obviously at the base, but in this case the base happens to be the top because the radius of a cone is not constant. The radius down here is not the same as the radius at the top. Okay. Now it says water pours into this tank at a rate of 2 cubic meters per minute. See the cube on the meters? What does 2 cubic meters per minute represent then? Well, meters cubed is a volume, and that's per time. So that's volume per time. So in other words, it's dV dt. dV dt is 2 cubic meters per minute. So then the question asks us to find the rate at which the water level is rising when the water is 3 meters deep. Okay, so think about pouring water into a cone. When you first pour water into this, the rate at which your water level rises goes very quickly because there's not a lot of room for that water to spread out down towards the bottom of the cone. So it will rise very quickly. But as it gets more room to spread out, the rate at which your water level is going to rise is going to slow down as you fill up this cup. So when we talk about the water level, if you imagine it to be, let's say, here or here or here, what you're actually changing is the height of that cone. So we are looking for dH dt for this particular problem, specifically when the water is 3 meters deep. So in other words, when h equals 3. So now that we have our knowns and our unknowns, what we need to do is get an equation that relates the two. So the volume of a cone is actually equal to 1/3 times pi r squared h. So that will relate our known to our unknown. If we go ahead and take the derivative from here, let's take a look at what happens. When we take the derivative of v, we get 1, but this is with respect to time, so that's dv dt, equals, I'm going to leave out the 1/3 times the pi. Now you need the derivative of r squared times h. Please keep in mind that is in fact a product rule. So we're going to take the derivative of r squared, which is 2r times dr dt, times the h, and add to that the r squared times the derivative of h with respect to t, dh dt. Okay, so if we look at this, dH dt is our unknown. That's okay. dV dt we know. As far as the r and the h go, I might be able to figure those out, but what I'm really concerned about is the fact that I have this dr dt sitting in here. And I have no mention anywhere in this problem as to how that radius changes with respect to time. It's not mentioned and it's not given, and that would be relatively difficult to figure out. I mean, finding a static quantity like a radius or a height is doable, but finding the rate at which something changes, unless it's given or what you're looking for, that's going to be pretty impossible. So turns out this isn't going to work out. So let's get rid of that for a second. In order to make it so that we don't get a dr dt when we take the derivative, what we're going to need to do is first eliminate the r, because as long as there's an r in this equation, we're going to end up with a dr dt when we take the derivative. So what we do is we look at our diagram, and what we notice is we have a height of 4 and we have a base radius of 2. And so what we notice is if we try and get a relationship between a radius and a height, so let's say this radius and say this height, so call it r and h. And these are supposed to be representative of any radius and height in here. What you start to see are two similar triangles embedded within each other. Well, when you have similar triangles, you can create a ratio. So we know that the radius over the height of each one should be equivalent. The radius part of the large triangle is 2, divided by the height part, which is 4, should be equal to the radius divided by the height of the smaller triangle. Well, what this ratio is going to allow me to do is it's going to allow me to solve for r. So 4r should equal to h, so that r should be equal to 1/2 times h. So that should be true throughout this entire cone. Well, notice now I have a replacement for r to put into my volume equation. If I replace it in, I get 1/3 times pi, and instead of r squared, I'll write 1/2 h quantity squared times h. Notice now I have volume as a function of the height. There is no radius in here, which means when I take its derivative, it's going to have no dr dt. So that was the goal. All right, So I'm going to clean this up just a little bit first. This 1/2 squared is 1/4. 1/4 times 1/3 is 1/12 times the pi. So we got pi over 12. And then here we have h squared times h for h cubed. Now take the derivative and watch the nice things that happen. Let's leave the pi over 12 out of the derivative for the moment. The derivative of h cubed with respect to time is 3h squared dh dt. So when I clean that up, the 3 will cancel into the 12, leaving me with pi over 4 h squared dh dt, and that is dv dt. Now I have something I can work with. We know that dv dt is 2 meters cubed per minute, and that should be equal to pi over 4 times the height squared. Well, now that we have this for all time, at this specific time, the height is going to be 3. So we'll have times 3 squared times the h dt, which is actually what we're looking for. So we solve for dh dt. And on the right side, this is going to be 9 pi over 4. So multiply both sides by 4 over 9 pi to cancel that out, times 4 over 9 pi. So when we're done, dh dt will be equal to 8 divided by 9 pi. And then our units, the height will be measured in meters, and the time will be measured in minutes. So that's 8 divided by 9 pi meters per minute. And if you want a decimal approximation for that, it's about 0.28 meters per minute. And that's how the height is changing with respect to time. Also known as how the water level is rising, specifically at the moment when the water is 3 meters deep. Okay, let's look at another example. This is going to be a two objects in motion type problem. And traditionally these have objects that are either moving apart from one another or moving towards one another. This one we have car A traveling west at 50 miles per hour and car B traveling north at 60 miles per hour. They're both heading for the intersection of their respective roads. At what rate are the two cars approaching one another when car A is 0.3 miles and car B is 0.4 miles from that intersection? So pause this for a minute and try and draw the diagram of what's occurring in this problem. So I'll assume you've drawn yours. So what's going on is you have car A moving west. So car A starts here and moves this direction. Car B is moving north, so it starts here and moves this direction. So this is car B. We have rates for both of those. We have 50 miles per hour and 60 miles per hour for car A and B respectively. So you can use any letters that you'd like. You can use A's and B's. I'm going to go ahead and use X's and Y's because I don't want to get confused on whether I'm talking about the car or the distance. X represents the distance from car A to that intersection. This is the intersection of the two roads here. So X is the distance between car A to that intersection. So since car A is traveling at 50 miles per hour, that means that dx dt is going to be equal to that rate. It's going to be 50 miles per hour. We'll talk about sine in a second. So that's 50 miles per hour. Car B is traveling north at 60 miles per hour. So its change, which I have labeled as y, dy dt, will be 60 miles per hour. But we do need to take sine into consideration. And what you have to keep an eye on is x represents a distance. Well, if car A is traveling to the west, is that distance getting larger or is that distance getting smaller? Well, it's getting smaller. So the rate at which it's changing is not 50 miles per hour, but negative 50 miles per hour. Take a look at y. Y represents the distance from B to the intersection. Is that distance getting larger or smaller? It's also getting smaller. So dy dt is also negative 60 miles per hour. Okay? You will have to make those choices when it comes to deciding the signs or the rates in your problems. It's why you want to make sure you have a very clear idea if you call something dx dt, you have to know exactly what x is and whether it's getting bigger or smaller. So the question is then asking us to find the rate at which the two cars are approaching one another when we have a couple of distances. So car A is 0.3 miles. So when x equals 0.3 and y is going to be 0.4 miles. Okay? But we're looking for at what rate are the two cars approaching one another. Okay, approaching one another means a distance between them is changing. But in this current picture, I don't have anything representing the distance between them. So I'm going to need some kind of representation for that. Well, what's the shortest distance between two objects? It's a straight line. So you're looking for, here's the distance from A to B. What you're looking for is how quickly is that distance changing when x is 0.3 and y is 0.4. So let me go ahead and call that distance something. I'll call it z. Okay? So in other words, what I am looking for is how that distance is changing. What dz dt is going to be equal to. Okay? So then we need a relationship between x, y, and z. And again, I see a single right triangle, and I'm trying to get a relationship between the three sides, and that is often a Pythagorean theorem. So I know that x squared plus y squared should equal z squared. Okay? So I'm going to end up taking the derivative of this, but I know that in this derivative I will have both a dx dt, a dy dt, and a dz dt. And I want to make sure that that's going to be okay. So notice I've been given the quantity for dx dt, I've been given a quantity for dy dt, and dz dt is what I'm looking for. So it's not like the previous example where I may have to get rid of one of my variables before I can start. I should be fine taking the derivative with all three variables in here. So I get 2x times its derivative with respect to time, dx dt, plus 2y times its derivative with respect to time, dy dt, equals 2z times its derivative with respect to time, dz dt. So first of all, you can divide both sides by 2. And all of those 2's nicely go away. And I'm going to go ahead and start inputting some values. We know that x is 0.3. So my x is 0.3 times dx dt, which we know is negative 50 miles per hour, plus y, which is 0.4 at this particular moment, times dy dt, which is negative 60 miles per hour. And that's going to equal z times dz dt. Now dz dt is what I'm looking for. I don't expect to input any numbers in for that. What I don't have at the moment, however, is a representation for z. But again, we have now frozen this at a particular moment in time, a particular moment when x is 0.3, y is 0.4. So in that case, we can go ahead and take a look at the right triangle that results. That's a horrible triangle, but bear with me. So we know that x is 0.3, y is 0.4. You can then calculate z by looking at 0.3 squared plus 0.4 squared equals z squared. That is one way to do it. Or if you remember your 3, 4, 5 triangles, if one leg is 0.3, the other is 0.4, the hypotenuse must be 0.5. If you don't know 3, 4, 5 triangles, that's fine. Just solve this for z and you should get 0.5. So z is 0.5, and then we just solve for dz dt. So we get negative 15. This one will be minus 24 equals 0.5 times dz dt. So that dz dt should be negative 78 miles per hour, since z is going to be measured in miles and your time is measured in hours. Notice again, it's a negative derivative. That's a good thing. Remember, A and B are both moving towards that intersection, which means z is getting smaller. So its derivative, the rate at which it changes, should be negative, or something's gone wrong. Okay, let's look at another one. Changing angle of elevation. We've got a video camera 2,000 feet from a launching pad at ground level is filming the liftoff of a space shuttle that is rising vertically according to the position equation, s equals 50t squared, where s is measured in feet and t is measured in seconds. Find the rate of change in the angle of elevation of the camera 10 seconds after liftoff. Okay. So again, you may want to pause this and see if you can come up with some of this on your own. But go ahead and do that now, but I'll go ahead and continue on. So we have a video camera. There's my camera. It's 2,000 feet from a launching pad. Now that's a constant value. That doesn't change. Your camera's vertical or horizontal position is not changing. It's just changing the angle at which it's watching the rocket. So on that launching pad, the rocket then has a vertical elevation. And we know that that vertical elevation is changing according to the equation s equals 50t squared. So the question is asking us to find the rate of change, so we will be looking for a derivative, in the angle of elevation of the camera. So the camera is trying to follow the rocket, and they're asking about the change in the angle of elevation. Well, the angle of elevation is that angle right there, and we're looking for how that changes. We're looking for d theta dt. 10 seconds after liftoff, so when your time is equal to 10 seconds. So we know we need some kind of equation to relate our knowns and our unknowns. So what I'm seeing is a triangle, specifically a right triangle. But this time, I don't just need to talk about the sides of the right triangle, I also need to involve an angle. And when you see an angle in a right triangle that you're trying to deal with, it's probably going to be some kind of trig function that you're going to have to use. Because trigonometry is what relates the angles to the sides of a right triangle. So what I see is an angle here, and the two sides that I want to talk about are opposite that angle and adjacent to that angle. That lends itself to using the tangent function. So what we're going to be able to say about this is that the tangent of this angle should be, that's a theta, should be equal to the opposite over the adjacent. So that's s divided by 2,000. Once we have that equation, we can take its derivative to start involving some of these rates of change. So the derivative of tangent theta with respect to time is going to be secant squared theta times the derivative of theta with respect to t equal to, it might be easier to take the derivative if you think of this as 1 over 2,000 times s. S over 2,000 is the same thing. So you'll have 1 over 2,000, that's the constant staying out front of the derivative, times the derivative of s with respect to t, so times ds dt. Okay. So we need to start seeing what we can replace or what we need to replace. D theta dt I'm not worried about because that is my unknown. That's what I'm actually looking for. Let's talk about this ds dt. Okay. We don't have any information about ds dt, but what we do have is s as a function of t. So if s equals 50 times t squared, and you take the derivative of this with respect to time, that should be 100 times t. That is the derivative with respect to time, so we don't need to use implicit differentiation for that. So that gives me the change in s with respect to the change in time for all times. Well, now that we've taken the derivative, we are specifically looking for this change at a time of 10 seconds. So ds dt, in that specific case, now that we're taking the derivative, evaluated at t equals 10, should be 100 times 10, which is 1,000. And there is a label on that. It should be feet per second. So we know that we have the secant squared of theta, I'll come back for that one in a moment, d theta dt equals 1 over 2,000 times 1,000, also known as 1/2. So we've actually cleaned this up quite a bit. We managed to get a replacement for ds dt. So now what we really need to find is this secant squared theta. And in order to do that, let me move up here so we actually have some room. What we have to keep in mind is that secant squared theta, because secant is just 1 over cosine, secant squared theta is just 1 over cosine squared theta, which in turn is just 1 over the cosine of theta quantity squared. That's a theta, not a 0. So if we could figure out the cosine of the angle, we would then in turn be able to find the secant of that theta squared. And now that we're talking about a specific time, we can examine a specific triangle to help us do that. What we know is that we have a right triangle. This leg is going to be 2,000. The vertical leg is going to be S, which is going to be 50 times t squared. Well, t at this particular moment is 10, so that's 10 squared. So this length is 5,000. We want the cosine of this angle. Well, cosine is the adjacent over the hypotenuse, which means I need the hypotenuse. But the good news is I can just get it using Pythagorean theorem. So we take 2,000 squared plus 5,000 squared, and that'll give me my hypotenuse squared. So the cosine of this angle, which is the adjacent over the hypotenuse, is going to be 2,000 for the adjacent divided by the square root of 2,000 squared plus 5,000 squared. So the cosine of this angle ends up being 2 over the square root of 29. Because the square root of 2,000 squared plus 5,000 squared, that's the square root of 29 million, which ends up being 1,000 times the square root of 29. So when you simplify, you get 2 over the square root of 29. So bringing it back to our equation, our secant squared is 1 over the cosine squared. So it's 1 over 2 over the square root of 29 squared times d theta dt equals 1/2. So when you solve this for d theta dt, you get 1/2 times 2 over the square root of 29 squared, to get rid of the 1 over, which means you get a 4 in the numerator, but then it's divided by a 2 down here. So you get 2 over the square root of 29 squared is just 29. So you get 2 over 29 for d theta dt. And then the label will be whatever theta is measured in divided by whatever time is measured in. And theta has to be measured in radians. And that's radians per the time is being measured in seconds. So that's 2/29ths of a radian per second for the rate of change in the angle of elevation. Notice it is positive because that angle will be increasing as the camera follows the rocket up. Let's take a look at another example. So I want to look at the velocity of a piston. Let's read the problem and then we'll take a look at a video that helps us see how a piston actually works. So the problem says in the piston shown, a 7-inch connecting rod is fastened to a crank of radius 3 inches. So the connecting rod is this rod right here. It's the gray rod in the diagram. That is a constant 7 inches. And then it's fastened to a crank, that's this, of radius 3 inches. So 3, so this is a crank. Sometimes it's actually a whole circle that goes around here. The radius of that crank is going to be 3 inches. So from the center to the outside, which is here, is going to be 3. This crankshaft rotates counterclockwise at a constant rate of 200 revolutions per minute. We are going to find the velocity of that piston when theta equals pi over 3. Let's take a look at a video of how a piston works, just so we have an idea of what's going on in this problem. Okay, so this is one example of a piston. It's certainly not the only kind. So in this diagram, this is your connecting rod, and this is your crank. Okay, so what you'll see in the animation is that the crank turns, that rod stays constant, and the radius around that crank stays constant. None of that changes. What's going to change is the distance between the piston and the crank, meaning from here to here. That is the distance that changes. It's the piston that's moving as this crank rotates around. So let me turn that back on so we see it. So the connecting rod is constant. The radius of that crank is constant. It's the position of your piston that changes. Keep that in mind as we take a look back at the problem. So in our problem, that means 3 is a constant and 7 is a constant. But this theta, which represents the angle in between the radius of the crank and the horizontal distance from the center of the crank to the piston, that's going to change. So this angle changes as this rotates around. And then the distance from the center of the crank to the actual piston is also going to increase and decrease. So this side is changing, this angle is changing, but these two sides are constant. So this type of example is going to require just a little bit more of a breakdown. We're looking for a velocity in this problem. So in general, a velocity is a change in position with respect to a change in time. Well, what is it that's going to be changing position? The 3 is a constant, the 7 is a constant. The position change occurs between the piston and the crank. So this is actually the position that changes. So when we're looking for the velocity in this particular diagram, we are looking for dx dt, assuming that this is what I have labeled x. So that's the start. That's what our velocity is. The other thing you have to be careful of with this is I'm starting to see a triangle that has a side of 3, a side of x, and a side of 7, and we're labeling this angle theta. But this is not a right triangle. And even if it were in this current position, remember this rotates. So this will not be a right triangle most of the time. So we're talking about an angle and some sides, and we can't use SOHCAHTOA because SOHCAHTOA requires us to be using a right triangle, which this is not. So when you have a non-right triangle and you're trying to deal with both the angles and sides of that triangle, usually what you're looking at is either the law of sines or the law of cosines. Now the law of sines involves ratios. It's the ratio of a particular angle and a corresponding side to another particular angle and a corresponding side. We're not dealing with two angles in this particular triangle. So that leads me to the law of cosines. And the law of cosines says the following. If you have a triangle and you label one of the angles theta, the side opposite that angle is labeled B, and the two adjacent sides to that angle are labeled A and C. Then the law of cosine says that the opposite side squared is equal to the squares of the two adjacent sides summed together minus 2 times the product of the two adjacent sides times the cosine of the angle. If you look, it almost starts off like a Pythagorean theorem looking type equation, but it's not. So that's the law of cosines, and in our particular diagram, that says that the side across from our angle is 7, and the two adjacent sides are 3 and x. And we are looking for dx dt. That's our goal. But specifically, we're looking for dx dt when theta equals pi over 3. So for our specific situation, we're going to have, according to the law of cosines, 7 squared equals 3 squared plus x squared minus 2 times 3 times x times the cosine of theta. Okay. Now this definitely cleans up. I mean, we can square the 7, we'll get 49. We'll have 9 plus x squared, that's a 9, minus 6 times x times the cosine of theta. So that's the equation that's going to relate our knowns and our unknowns. Our unknown being an x and our known being a theta. But now there's one extra point that we need to make sure we're clear on. All of our units have to be consistent. And so theta, which is going in our cosine function, is measured in radians. If you notice, the other given piece of information is that the crankshaft rotates counterclockwise at a constant rate of 200 revolutions per minute. Now, if you notice, that is a rate. It's how that is rotating with respect to time. but it's the wrong label on there. We need to get this to talk about radians, not revolutions. So the bad news is we have to do the conversion. The good news is the conversion actually isn't that complicated. What we know is that 200 revolutions occur per every 1 minute. Okay? And we want to be able to talk about this in terms of radians. So what is the relationship between a revolution and radians? Remember, this is a circle. So if you have 1 revolution, how many radians does that complete? Well, it's 2 pi. So in order to convert this, all we have to do is keep in mind that 1 revolution is equal to 2 pi radians. Labels cancel the same way numbers do. So here, revolutions will cancel revolutions, and what you'll end up with is something that is measured in radians per minute, and that's perfect for us. That's 400 times pi per 1 minute, and that's radians. So in other words, that is how the angle changes with respect to time. In other words, that is d theta dt. d theta dt is 400 pi radians per minute. So now when we go to work with our equation, we're going to take its derivative. The derivative of 49 is 0. The derivative of 9 is 0. The derivative of x squared, remember this is with respect to t, so that's 2x dx dt, minus, now I need the derivative of 6x times cosine theta. So you're going to need a product rule here. It's 6x times cosine theta. Also be careful of that negative sitting out front. I'm going to leave the negative out and open up a set of parentheses. You could also leave the 6 out. That would be a completely legitimate way to go about this. So I'm going to take the derivative of 6x, which is 6 dx dt, times cosine theta, plus 6x times the derivative of cosine theta. The derivative of cosine theta is going to be negative sine theta, so this is going to be a minus now, times d theta dt. So we actually have substitutions in for a lot of this. We have 0 equals 2. I'm going to leave the x as an x for just a moment. We'll come back for that. Dx dt is what we're looking for, so we don't expect to plug in for dx dt. We'll have minus 6 dx dt, which again, we don't expect to plug in for that, but we have cosine of theta. Now that we've taken the derivative, this is good for all time. We're specifically looking for the time when theta equals pi over 3. So that will be the cosine of pi over 3. And then this will turn to a plus, because I'm going to distribute the negative to it. 6 times x, again, I told you we'll come back for x in a second, times the sine of theta, and again, theta is now pi over 3, times d theta dt, which we just calculated as 400 pi, and that's radians per minute. So now we need to real quick talk about x. That's pretty much what we have left to solve for. dx dt is our unknown, so we're not expecting to solve for that until the end. So we got to figure out x. And for that, we need to go back to our original equation. Keep in mind, this equation is good for all x values. We are specifically looking for x at the moment in time when theta is equal to pi over 3. So from the original equation, before we took derivatives, we know that 49 should equal 9 plus x squared minus 6x times the cosine of pi over 3. But remember, the cosine of pi over 3 is 1/2. So this ends up being, if I put everything on one side, x squared, the 1/2 times the 6 will get me minus 3x, and then if I pull the 49 over and subtract it, it ends up being minus 40 equals 0. So notice we can solve this for x. It is a quadratic. We cross our fingers, we hope it factors. If it doesn't, no big deal, we just use quadratic formula. In this particular case, it does in fact factor. 2x minus 8 times x plus 5, which says this quadratic has two solutions, x equals 8 and x equals negative 5. But given that this x is representing that distance between the piston and the center of the crank, then x equals negative 5 is not a possibility, and x equals 8 is our only solution to the quadratic relevant to this particular application. So x equals 8 is going to go in here. So we're going to get 0 equals 2 times 8, yes, that's 16, times dx dt minus 6 times dx dt times the cosine of pi over 3. Again, the cosine of pi over 3 is 1/2. So that's 3 dx dt plus 6 times 8 times the sine of pi over 3, which is the square root of 3 over 2, times 400 pi. And while that's not very pretty, the only variable over there is the dx dt. That's the only thing we have to solve for. So we know that this is 16 dx dt minus 3 dx dt, so that's 13 dx dt. And then this is 48 times 400, but divide it by 2 and then multiply it by the square root of 3. So that's 9600 square root 3 times pi. Okay? So when you solve this for dx dt, you just subtract the 9600 pi times the square root of 3 over and then divide by 13. So that tells me that dx dt, also known as the velocity of this piston, is negative 9600 pi square root 3 divided by 13, which if you get a decimal approximation for that, it's about negative 4018, and then we need a label on that. This is dx dt. X, which is our linear measurement, is measured in inches in this particular problem, and then dt is our time, and that's going to be per minute. So the velocity of this piston at the moment when that angle is equal to pi over 3 is negative 4018 inches per minute. And think about something. That came out negative. Does that make sense? Well, when this angle is pi over 3, and in case you can't remember, that's 60 degrees, so this is about a good representation of what it would be. This is rotating in a counterclockwise direction. Well, if this is rotating counterclockwise, then what is happening to x? Is it going to get bigger or is it going to get smaller? Keeping in mind that as it rotates from its current position counterclockwise, the connecting rod is also pulling this direction, which means the piston is going that way. So what's happening to x? Is x getting larger or is x getting smaller? Well, it's getting smaller. So it makes absolute sense that its derivative at that particular moment in time will be negative. So those are some examples of related rate problems. Generally, these start to fall under a very few headings. You get filling tank problems that may also be, instead of filling a tank, you are taking water out of a tank. Doesn't have to be water, of course. So you could be filling a tank or emptying a tank. That's one classification of problems. It is very common to have right triangle problems. We saw a couple examples of those. Some where you were looking to find how the relationship between the sides were changing, and some where you were looking at how the relationship between a side and an angle were changing. There are problems that involve non-right triangles, which are traditionally going to be a law of cosines or a law of sines problem. Those are not the only classifications, but you start to be able to categorize these related rate problems. So really the only way to get very good at them is to do lots of them. So especially in this section, please make sure you're doing as many practice problems as you possibly have time for.